Greetings. My name is Philip Hanston, and I was greatly looking forward to meeting with you in person at the venue in Germany, but alas, it was not to be. I'd like to dedicate this lecture to Professor Hartmut Derendorf, a man whose scientific excellence was matched by his humanity. He was a great human being. Okay, now I'm going to screen share and see if I can show some slides. Okay, before we begin, I have to warn you, Yoda, our Norwegian forest cat, is sleeping right over there on the desk. So if you hear some noises in the background, that means he woke up. Now, I'm sure you found the title of this talk a little curious. Why philosophy? Why should scientists and healthcare professionals worry about philosophy? Well, philosophy is great for thinking deep thoughts like the meaning of life. This is what happens when you let your dog eat your philosophy homework. But that's not what I'm talking about here. I'm thinking in more practical terms. And I'm going to try to convince you today by giving you 8 reasons why philosophy is useful for science in general and also for drug interactions in particular. The first one is thinking clearly. Physician philosopher William James, who was not prone to staring into sunsets. He was a hard-nosed scientist, and when somebody asked him, what is philosophy? He called it a peculiarly stubborn effort to think clearly. And I like that definition. That's my favorite definition of philosophy. Bertrand Russell, another person not prone to staring into sunsets, acknowledged that many men under the influence of science or in practical affairs are inclined to doubt whether philosophy is anything better than innocent but useless trifling, hair-splitting distinctions and controversies on matters concerning which knowledge is impossible. So he acknowledged that many people don't, especially scientific people, don't think philosophy is of any use. But he pointed out that the man who has no tincture of philosophy goes through life imprisoned in the prejudices derived from common sense, from habitual beliefs of his age or nation, and from convictions which have grown up in his mind without the cooperation or consent of his deliberate reason. So there's plenty of philosophy that is practical, and that's what Bertrand Russell is saying. Second reason to study philosophy is scientific inspiration. For some scientists, philosophy has been a central reason for their success. You know what this is? This is Einstein's desk on the day that he died. So if somebody gives you or hassles you about having a messy desk, you can tell them it's the price of genius. But notice up in the upper right-hand corner, there's a philosophy journal up there, and that it was not surprising to me. Here's a quote from Einstein, a letter he wrote to a colleague. He said, quote, "It's very well possible that without these philosophical studies of David Hume and Ernst Mach, I would not have arrived at the solution for relativity theory." So he made it clear that philosophy was critical for his discoveries. Same goes for Sir John Eccles, who won a Nobel Prize in medicine, and he credited much of his success to the philosopher Karl Popper, as did another Nobel Prize winner in medicine, Sir Peter Medawar. He said the same thing about Popper. So the most accomplished scientists often embrace philosophy, not just the 3 I've mentioned here, but many others as well. Now let's look at some examples using philosophy to deal with specific interactions, like making decisions in the presence of uncertainty. There's uncertainty in almost every drug interaction you can think of. And so this is something we have to deal with a lot. Now, some decisions are easy, are slam dunks. If somebody offers you these 4 ice creams, obviously you take one of the chocolates. There's no excuse for vanilla ice cream. So this is a slam dunk, and some drug interactions are slam dunks as well, where the evidence is so strong and so overwhelming, that's in column A there, that we know that we should probably try to do something about the interaction. Now I have certainty in quotes, of course, because we never achieve absolute certainty on these drug interactions. Here's an example of a slam dunk interaction called colchicine and clarithromycin. This was a series of 116 patients on colchicine and clarithromycin. Note that the fatal toxicity from colchicine was 6 times greater when the overlap was greater than 2 days than when it was 2 days or less. So we should make every effort to avoid using this combination of drugs. Now, there aren't that many slam dunk drug interactions. There aren't that many that fall into that category. Most of them fall into this middle category that's represented by B here. They're important enough to consider, at least in some patients, but they're not slam dunks. Now, admittedly, there are some drug interactions for which the evidence is insufficient to even reach the threshold for action, and these are interactions that shouldn't even be on clinical decision support systems. Unfortunately, sometimes they creep onto those systems when they shouldn't be. There's also a problem sometimes because people disagree whether it should be B or C, whether we've reached the threshold for action for it or whether we have not. And a good example of that is tamoxifen and 2D6 inhibitors. This has been very contentious over the past couple of decades. There have been partisans that have dug in on both sides of this debate. One group is saying that it's B, that it clearly is clinically important and we need to worry about it. And the other people are saying, forget about it. It's not important. The mechanism or the proposed mechanism for this interaction is that tamoxifen is a prodrug. People agree on this. And in order to get endoxifen, which is the active metabolite of tamoxifen, 2D6 is necessary. So it would make sense, theoretically, that anything that reduces CYP2D6 activity should reduce endoxifen plasma concentrations and therefore may in fact reduce its efficacy. And in fact, when they started doing studies to look at this, many studies like this one from David Yerlink's group up in Toronto found just that. This was a group of women with breast cancer on tamoxifen and SSRIs, and paroxetine was clearly associated with an increase in breast cancer mortality. And you note there that as the overlap increased, the mortality increased along with it. Now, there are a number of other studies found similar results of reduced tamoxifen efficacy in the presence of potent 2D6 inhibitors. Unfortunately, some other studies did not find this. And this is from one of the people who did not find it. They said available studies do not appear to support a negative impact of 2D6 inhibitor use on breast cancer recurrence and mortality in women using tamoxifen. Now, when I looked at the references that they cited to support this statement, I was astonished at the list, how inaccurate the lists of 2D6 inhibitors they used in order to correct for their data were terrible. In one case, of the 30 2D6 inhibitors they claimed, only 10 of the 30 were actually 2D6 inhibitors. So there were a lot of problems with some of these negative studies, and not just erroneous lists of 2D6 inhibitors, but some of them had weren't done long enough. Some lumped premenopausal and postmenopausal patients together. Some of them used improper pharmacogenomic tests. Some measured total mortality instead of breast cancer mortality, which wasn't optimal. Yet some people still deny that this interaction exists. So what do we do in the presence of this kind of debate and controversy? Well, we consult the enduring wisdom of Blaise Pascal. Now, Pascal was one of the most amazing intellects, in my opinion, one of the most amazing intellects in human history. He was a mathematical genius. He was a scientist. He was co-originator with Pierre de Fermat of probability theory. And he was also, for us today, the most interesting thing for most of us is he had profound insights into the human condition, which was found in his book, Pensée, which is the primary book that people read from Blaise Pascal. But Pascal didn't stop there with making me feel inadequate. He also spent an enormous amount of time and money helping the poor. So he was quite a guy. Given all of his accomplishments, it's kind of sad that he's known best for Pascal's wager, which was only a minor part of his intellectual output. Some people think it was just a throwaway line in his Pensée. It's not a profound theological argument, but the concept behind it is perfect for making decisions in the presence of uncertainty. So here's a decision matrix to show his wager. In his day, the feeling was that if God exists and you believe in God and act accordingly, you would have eternal bliss. On the other hand, if God doesn't exist but you think he does and you act accordingly, it's you've made a type 1 error. You think something exists that doesn't, so it's really no big deal. In his that's in orange. In purple, if God does not exist and you don't believe in God, obviously you got it right. The issue is moot. But this is the one that Pascal said we should try to avoid, where God actually exists, but we don't believe, and we've made a type 2 error that results in our eternal damnation. Now, in Pascal's day, this is what they thought it was going to be like if they ended up being bad and going to hell. I mean, it doesn't look like much fun, maybe for the demon, but not for many other people. Now, I've checked this on Google, and not many people believe in hell these days, but I'm willing to make one exception, and that would be for the guy who invented labels that cannot be removed from garbage cans. I think going to hell might be appropriate for him. Now, I know that's not very nice, but so let's look then at tamoxifen drug interactions and see if we can apply Pascal's reasoning to this. So if the question at the top there is, can 2D6 inhibitors reduce tamoxifen efficacy? If the answer is yes, they can, the interaction is real, and we believe it and take appropriate steps, we've improved patient survival. That's a good thing. If it doesn't exist, if the interaction is not real, but we think it is, and we take unnecessary precautions, we made a type 1 error, it's no big deal. Took a few extra precautions. In purple down in the lower right, if the interaction is not real, and we don't think it's real and we don't do anything, it's moot, as with the God thing. On the other hand, the one we really need to avoid is the type 2 error, where the interaction is real, but we don't believe it and we take no precautions. In this case, it can result in cancer recurrence and death. Now, for some reason, many scientists seem far more worried about making a type 1 error, where it's no big deal if they're wrong, instead of making a type 2 error. I mean, they worry more about that than they do about making a type 2 error, where it could result in cancer recurrence and death. That's a strange way of approaching this problem. I should think they would be more worried about people dying from the interaction than them making a mistake. So Pascal's law of drug interactions, and this is my formulation, not an official one. The scientific certainty needed to reach the threshold for action or a drug interaction can be less than 50-50 if the risk of a type 1 error is potentially life-threatening, and avoiding a type 2 error is relatively easy. Assume the drug interaction is real until proved otherwise. So with tamoxifen, it's very easy to get around this interaction. You can use venlafaxine or citalopram or some other SSRI instead of paroxetine or one of the SSRIs that inhibit 2D6. And that's a very easy thing to do. So it's very easy to avoid the interaction. And then if it turns out it's actually real, which I happen to believe it is, then we have done the right thing and potentially saved lives. Now, another a very similar example is the question of, do antibiotics increase the risk of unintended pregnancies in women taking oral contraceptives? The first cases were reported in 1975, and over the years, partisans emerged on both sides, and evidence was presented on both sides. And as with tamoxifen, most of the negative studies had a lot of flaws in them. And yet a number of people claimed that they had proven that this interaction does not exist. And so for a half a century, this started in 1975, for half a century, the naysayers and believers argued about this drug interaction. And unfortunately, the naysayers won the battle. And currently, despite all the flaws in all those negative studies, the naysayers won the battle. And currently, most drug interaction sources and drug agencies claim that this drug interaction has been disproven and you don't have to worry about it. So, but for 45 years, I've been pleading for a Pascalian solution of avoiding a type 2 error for this. Unintended pregnancies can be life-changing. And the naysayers' arguments were based on flawed information. So I argued that women should be provided the information, including the fact that it's controversial, and they should be given the opportunity to make the decision for themselves as to whether or not they want to take extra precautions. It seems like the interaction should be presented in that way to them. Then the landscape of this interaction changed substantially last August of 2020. And the results, this was a database review in the United Kingdom, and they looked at the odds ratio for unintended pregnancy, and they found with antibiotics, hormonal contraceptives and antibiotics in orange in the middle, was 6.7 compared to control drugs. And for enzyme inducers, it was 13. Now, the enzyme inducer hormonal contraceptive interaction is not controversial. Everybody agrees that that happens. So that was odds ratio of 13, but the antibiotics odds ratio was about half that. So if we had been taking, now, even more important than the results of this study, which are very interesting, is the e-supplement that Aronson and Ferner added, which you can get online. And that is, in my opinion, the best discussion of this interaction that's ever been published, ever. They go through pretty much every study that's ever been published on the interaction and critique it and assess it and analyze it. So if you really want to find out about this interaction, read their article, but especially read their the e-supplement for it. So if we've been taking the philosophical Pascalian position for the past 45 years, I'm convinced that many women would have avoided unintended pregnancies from this probable interaction. Okay, another problem that can be addressed by philosophy is the problem of induction. David Hume put a spotlight on this issue many years ago. Spent a lot of time talking about the process of induction. If you remember, Hume is the one that Einstein gave credit to for his relativity theory. Reading Hume was very helpful to Einstein. So what is induction? I heard, by the way, I'm not talking about enzyme induction. We're talking about philosophical induction, okay? So let's assume that you see a number of individual cases of people getting two interacting drugs together. We see what happens, and through inductive reasoning, we come to a general principle that generally when people get these two drugs, this is what happens. And then after we form the general principle, then we take that and apply it to later individual cases. Now, this is a simplified version of induction, but it kind of gets the general point across. But we can get in, so it's very useful. Induction is very useful in dealing with drug interactions, but we can also get into trouble using induction if we're not careful. For example, assume there's a potential interaction between drug A and drug B, and you as an individual practitioner see, say, let's just say 30 or 40 patients getting the two drugs, and you don't observe any adverse consequences. Your usual conclusion is going to be that this interaction is not clinically important. But it could be, that could be the answer, that the interaction truly isn't clinically important, but it also could be that you've made an error of induction. So there are a lot of reasons why using our casual observations, our clinical experience, may not give accurate results. Too few observations. In many cases, you have to see a lot more people on the combination before you're likely to observe it. Lack of follow-up. In other words, you may not really know it. The patient may have experienced an adverse outcome, may go to the emergency department, but you may not even be aware of that. And also there are high impact, low probability HILP drug interactions that happen. They may be even severe, but they happen so infrequently that no individual practitioner sees enough cases. And you really need epidemiological studies to assess them. And a good example of that would be SSRIs combined with anticoagulants, various kinds of anticoagulants, actually. This one happens to be warfarin. It's a cohort study where they looked at people on warfarin and the outcome they looked at was hospitalization for major hemorrhage. And as you can see on the right, SSRIs did increase the risk of hemorrhage, but it wasn't a terribly large increase. The absolute value of hemorrhage, the risk was not very high. Note that in the middle there that tricyclic antidepressants did not increase the risk of hemorrhage. But an interaction that happens that infrequently, you cannot rely on your personal experience to detect it. For an adverse drug interaction that occurs once in 1,000 cases, you'd have to study 3,000 people to have a 95% chance of observing the event. Let's look into a little more detail on HILP drug interactions. Here's an example that's not a drug interaction. Let's say a giant asteroid is headed for Earth and it's going to wipe out most life on Earth. That's high impact, literally. But a drug interaction example would be a cerebral hemorrhage after giving systemic epinephrine to a patient on a beta adrenergic blocker. Now, what happens here is if you give systemic epinephrine, it has to be that. Normally, there's vasoconstriction and vasodilation, that there's somewhat of a balance between those two. But if you give a non-selective beta blocker, you relatively block the vasodilation, leaving unopposed alpha vasoconstriction, and this results in a hypertensive response. Now, this has caused cases of stroke. This is an extraordinarily well-documented interaction. We have case reports of disasters. We have pharmacodynamic studies in healthy subjects and patients. We have all kinds of data to demonstrate. We know what the mechanism is. So this is one of the best documented drug interactions that we have, period. But we rarely see stroke as an adverse outcome from this interaction. So why would that be? Well, I'm using James Reason's Swiss cheese concept. A lot of people have used this for a variety of reasons. But if you have the epinephrine beta blocker as the hazard up in the upper left, and down in the lower right, you have stroke as the probably the worst outcome from this interaction. So between the hazard in the upper left and the adverse outcome in the lower right, there are a number of these slices of Swiss cheese. And by the way, if you have any Swiss cheese that's actually any of these colors, please don't eat it. But if you give epinephrine, systemic epinephrine to somebody on a beta blocker, one of these defenses usually stops it before it gets to the person developing a stroke. But every now and then, as we know from case reports, every now and then the holes line up and there's a defect in every one of these slices of Swiss cheese and the patient does develop a stroke. But why does it happen so rarely? Well, first of all, the indication for epinephrine can block the interaction. Here we have it stopping at the very first slice of Swiss cheese. If the epinephrine is being used to treat anaphylaxis, you do not see this problem. And so it's not something that you should worry about if the person has anaphylaxis. The biggest reason it doesn't progress any farther is the dose of the epinephrine. The vast majority of people are getting an insufficient amount of epinephrine to produce a significant interaction. Also, the type of beta blocker is important. Cardioselective beta blockers and mixed alpha beta blockers don't seem to cause this problem. And it makes sense that they wouldn't, because most of the time, not always, but most of the time, cardioselective beta blockers do not block the vasodilatory effects of systemic epinephrine. So you still have that balance between vasodilation and vasoconstriction. And this is very well studied. You typically see only a small effect on blood pressure. And even if it gets all the way down and the person has an acute increase in blood pressure, one can presume that the reason why even that rarely produces a stroke is that most people aren't susceptible to that they can withstand an acute increase in blood pressure without developing a stroke. And it's only very rarely that a person has there's a hole in every one of those slices and the person ends up with a stroke. Okay, another reason to study philosophy is the prediction fallacy. As Niels Bohr, physicist Niels Bohr pointed out, prediction is very difficult, especially if it's about the future. Now, we do pretty well with the physical sciences. We're able to send people to the moon with great precision. Things like physics we do pretty well with, but in the biological sciences, we're not nearly as good at predicting. Colchicine, for example, we already talked about this once. It has some very nasty drug interactions that are potentially fatal. And one of the problems with colchicine is that well, and this actually applies to drug interactions in general, but there's a huge variability from one person to another in the magnitude of the interaction. Now, these bars represent colchicine area under the curve with and without the interacting drug. And the dark purple are people, the person that had the smallest effect, and the light purple is the subject that had the largest effect. Now, most of these studies involve between 20 and 24 healthy subjects. Healthy subjects, variability is probably even worse in patients. But notice the ritonavir there. The healthy subject with the smallest increase in colchicine AUC was 54%, and the person with the largest was 924%. It's a pretty large variability. Again, we see this with virtually every drug interaction that's ever been reported. Now, one of the manufacturers for colchicine came up with some dosage reduction scheme. It's kind of a one-size-fits-all dosage reduction scheme where if you add this drug, then you reduce the dose of colchicine by that amount. And that's fine, except that in most cases, it's far better to avoid the interaction rather than make this kind of a dosage reduction. So why do I say that? What's my justification for saying that? Well, if you look at A at the top, this is before the 3A4 PGP inhibitor is started. Let's just, for argument's sake, say all of them are therapeutic in green. If you add the 3A4 PGP inhibitor and you don't do anything, you don't change the dose of colchicine, it's true that some of those people will become toxic in red, and some people will almost certainly die. That's the ones in purple. So if you reduce the dose, it may sound good at the start, but if you really think about it, because of this high variability, if you reduce the dose of the colchicine when you start the 3A4 PGP inhibitor, because of this variability, some people are going to almost certainly be subtherapeutic in gray. Sure, some will remain in the therapeutic range in green, but you're still going to have some toxicity, and possibly even some people will die from the interaction. So it's not an optimal solution. And if you say, well, let's reduce the dose of colchicine so that nobody gets toxic, well, then you're going to have an acceptable number of people who are subtherapeutic. So far and away, the better way of handling this is to avoid the combination if you possibly can. And this can almost always be done. You can either find an alternative drug for the drug causing the interaction with colchicine, or you can stop the colchicine during the period of time the other drug is being given, or you can come up with some other method of avoiding giving the combination. Okay, now I'd like to talk about a few informal fallacies. I'm only going to talk about 2 or 3. There are many, many more we could discuss, but there's simply not time. The first one is the post hoc fallacy. And the classic example, oh, by the way, this post hoc comes from the Latin post hoc ergo propter hoc, which is after this, therefore because of this. And it's called shortened to the post hoc fallacy. Here's the classic example of the post hoc fallacy, the rooster taking credit for the dawn. Every morning he wakes up, he crows, pretty soon the sun comes up and he decides, well, it must be me. I'm probably the one who caused the sun to come up because every time I crow, the sun comes up. A drug interaction example of this, this is an actual case, it's an old case, but it's a real case where this guy was on chronic warfarin. He went fishing, his prothrombin time doubled, came back down, he went fishing again, there was a doubling of his prothrombin time. The people reporting this couldn't come up with any reason why this might have happened. Obviously, it wasn't the fishing itself. My best guess is it was that 6-pack of beer that he drank while he was fishing. That might have had something to do with it. Another fallacy that we need to consider is the conventional wisdom fallacy. And as Michel de Montaigne said, people are carried away by the common opinion, which always follows the leader like a flock of cranes. And by the way, Montaigne is a wonderful source if you want to instill some intellectual humility in yourself. Read his essays. It's a very thick book. I have it back there on the shelf. And it's really a good way to acquire that trait. Okay, one example of conventional wisdom that has gone astray is protein binding. Now, in the early days of drug interactions, back in the 60s, 70s, 80s, people felt that protein binding was a major cause of drug interactions. We now know that it's not common at all. It can occasionally be a problem, but usually not. Yet still today, people will invoke protein binding displacement as a cause for a particular drug interaction. Appeal to common sense is another one of the fallacies that drug interactions can fall afoul of. And I'd like to use this example. It's what I call the highway metaphor fallacy. People assume, well, first of all, if you're dealing with cars, as in this photo, the more cars that are there, the slower the traffic flows. You know, the cars coming towards us are going way slower than the ones on the right going away from us. And they use this, apparently, they use this idea to say, well, if a drug is metabolized by a particular enzyme, then it must necessarily inhibit that enzyme. But that just simply isn't necessarily true. Sometimes they do, but there are many, many exceptions where a drug doesn't, where it's metabolized by this enzyme, but it doesn't actually act as an inhibitor. Now, this highway metaphor fallacy is what got the tamoxifen people into some difficulties, where they assumed that was the case, and they used drugs that were metabolized by 2D6. They thought, well, they must inhibit 2D6 then, and they used them in making corrections for their data, which ruined their data basically. Okay, the last one, we're on the home stretch here. Recognizing epistemic responsibility. This is another philosophical concept. And the definition of this is we have a responsibility to consider the empirical evidence and use rational thought as a guide to our action or inaction. And unfortunately, Yoda the cat is awake now, so I may have to be pushing him away from my computer. Okay, we have a responsibility to consider the empirical evidence to use and use rational thought. And William K. Clifford, a brilliant mathematician, philosopher from the UK, had a thought experiment that was very interesting. And I'm going to read this so I can get it in a succinct way for you. There we are. So he has this thought experiment to show epistemic responsibility. He didn't actually call it that in so many words, but that's really what he was talking about. So, and he said, suppose a ship full of immigrants is about to sail across the ocean, and the ship owner, this is my shortened version of his thought experiment. Okay, ship's headed over the ocean. The ship owner knows the ship is in bad repair and should be inspected before sailing, but it would be expensive. So that against the evidence, he knows that he should have it inspected, but against the evidence, he convinces himself it will be okay. The ship sails, sinks mid-ocean, everybody dies, but the ship owner gets his insurance money for the boat, for the ship. Clifford first asks, the first question Clifford asked is, was it unethical for him to do that? And everybody who's not a sociopath would say, yes, that was unethical. He knew the ship needed repairs. He sent it over there anyway, and it sank. But then he asks a more difficult question. He says, well, what if the ship had not sunk and it had made it across, and many, many more times back and forth after that? Then was the ship owner culpable? And you probably know what I'm going to say here. And what Clifford said was he's absolutely as culpable if the ship made it across many, many times as if it did not. So the outcome basically makes no difference at all as far as the ethical nature of his decision to let the ship go. Just because he got lucky in that second scenario where it didn't sink, it didn't make his decision any better. So this is Clifford's law, and this again is me saying this is Clifford's law. This is not an official law by any means. Once an action is done or not done, it is right or wrong forever. If you have considered the evidence carefully and objectively and you have done your best, you can rest easy no matter how it turns out. And this applies to drug interactions, but it also applies to if you're picking a vacuum cleaner or any decision that you make. If you do your best and you consider it objectively, you don't have to worry. It's a very liberating. Clifford's Law I use at least weekly. It's a very liberating concept. But with regard to drug interactions, how can we apply it to that? Well, allopurinol and thiopurines, the historical perspective is that Gertrude Elion, who, by the way, could not get a job early on because she was a woman, but she finally got a job. And when she did get a job, she ended up developing all of these drugs. And she also, for our purposes, in 1963, published a paper showing that allopurinol could inhibit mercaptopurine metabolism. But unfortunately, even though she demonstrated that in 1963, we have seen countless, dozens of reports of people in those ensuing almost 60 years of people being harmed, severely harmed and dying from this drug interaction. Here's one that actually Dave Yerlink, is from a Canadian newspaper that Dave Yerlink alerted me to. Pharmacists, this is the headline said, pharmacist failure to check drug risk lead to horrible death. They had a picture of the woman who died, her son, and the pharmacist in the paper. BC woman's demise exposes dangers of alert fatigue among pharmacists. Now, the same physician wrote for both medications. It was mercaptopurine and allopurinol. Same physician wrote for both, so he certainly should have considered this as well before he wrote for the second drug. So I looked to see, after seeing this, I thought, well, okay, let's see if there are any recent reports. So just a few weeks ago, I went on PubMed and I searched for this interaction, and sure enough, 6 months ago, here was a man who developed pancytopenia following allopurinol and azathioprine. And just this year, in 2021, another case of severe anemia from azathioprine and allopurinol. So no, we have not stopped killing people and causing severe harm, life-threatening drug interactions, even though this interaction was discovered by Gertrude Elion in 1963. I'm glad she's not still alive to see what's going on. So the question is, will we ever stop killing people with allopurinol and thiopurines? I always bring this up with my students. I teach a class this is what you're getting today is a 35-minute version of an entire class. But I try to get them angry about this, so maybe one of them will at some point figure out a way that we can stop killing people from this drug interaction. So it follows Gide's law. André Gide actually won the Nobel Prize in Literature, and he said, and this Gide's law again is my formulation, not official. Everything that needs to be said has already been said, but since no one was listening, everything must be said again. And this definitely applies to this drug interaction and actually many other drug interactions, but it applies to literature and a lot of other stuff besides science as well. So I ran across this gem when I was reading André Gide's Autumn Leaves. At the beginning of Autumn Leaves, he has a whole bunch of really profound aphorisms, and this was one of them. So to come full circle to address the question that I brought up at the very beginning, why should scientists and healthcare professionals worry about philosophy? Well, I personally believe that applying philosophical principles, not all drug interactions need it, but some do. And for those drug interactions that do need the application of philosophical principles, I think we can improve patient care and maybe even improve lives. Plus, philosophy, for me personally, is enormously fun. Some of the profound questions that philosophy addresses are really intellectually very stimulating and worth considering. So I highly recommend it. Thank you very much for your attention.